I'm a PhD student here in the probability group in Oxford. And yeah, as Pravahi says, I'm going to be giving 2 one-hour talks about probability and game theory. So this first talk is going to be more about the probability, and then Thursday's talk is going to be more about the game theory. So we're going to start with some questions to get everyone's thinking about probability. So can everyone type in the chat to let me know that they can see the chat and everything? Because we're going to do some, people are going to type their answers there. Okay, cool. Okay, nice seeing that people can see, that'll do. Okay, so what we're going to talk about. So today we're going to be doing some introduction to probability. So we're going to talk about things like the law of large numbers that you might have heard of, something called the central limit theorem. I'm going to tell you what all of these things are. And the aim of the game is going to be to apply these tools to find out why roulette is a losing game, as in why the house has an edge when you play roulette in the casino. So to start off with, let's start off with a thought experiment. So we have 2 dice, 2 fair 6-sided dice, and we're going to roll both of them, and then we're going to count up how many spots there are on the top. And the game we're playing is that you get paid £1 per every dot on the dice. And I'd like to know, what is the most you'd be willing to pay to play this game? So have a think about it, see what you think, and type some answers in the chat when you've got some ideas. Okay, cool. I'm seeing a lot of people saying 6, seeing a lot of people saying £6.99. Does anyone want to explain why they're saying, okay, someone's saying under 7, between 4 and 6, lots of different answers. Does anyone want to have a go at explaining why they're saying what they've chosen? If not, we can move on and I'll explain the... Yeah, exactly right. So the average of 2 dice is 7. So what I'd like to think about, first of all, is how we're defining average. So what a probability person would call average is something called the quote-unquote expected value of a random outcome. So this is the average outcome when you weight by the different probabilities that the value can take. So for example, if we call x the number of spots that are showing on a single dice, then the values this can take are 1, 2, 3, 4, 5, or 6. And then the expected value is the average of those quantities, which is 3.5. Does that make sense to everybody? Thumbs up in the chat if everyone's happy so far. Okay, seeing some thumbs. That's good. Okay. So whenever you hear expected value, you just need to think average. So if you were to pay £6.50 to play this game, you would be winning on average 50p every time. Or if you paid £7.01, you'd be losing on average 1 penny every time you play the game. So that's the key concept, the expected value of your winnings being 50p. Okay, so we're going to look at a more general formula for expected value. So in our case, we had a dice that could take different values 1, 2, 3, 4, 5, and 6. And each of those happened with the same probability, that probability being 1 over 6. And so we just added up 1/6 times 1 plus 1/6 times 2 plus blah, 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 up to 1/6 times 6. Okay. In the general case, someone says they come. Everyone else can see the slides, right? Can I get a thumbs up if you can see the slides? Okay. I think that might be... I think that's not my problem on my end then, so I'm just going to carry on. Okay, so the general formula is if you can take values A1 up to AN, and that AI happens with probability PI, then the expected value is the weighted average of the values of A. So that's A1 times P1 plus A2 times P2 plus ... plus AN times PM. Okay. So as our first application of the concept of expected value, we're going to take a look at the game called European Roulette. So this is like a common game you play in the casino. The way it works is there is a wheel with 37 numbers, the numbers 0 up to 36. And we're going to do the simplest case where on your turn, you put one counter on a single number, either 0, 1, 2, or any number up to 36. And then the operator spins the wheel and the ball spins around and around and around and lands. And if you guessed correctly, you're going to get back your £1 plus an original 35 and plus an extra 35. And if you guess incorrectly, you're going to get 0 back. So, first of all, answer in the chat. Does it matter which number we guess in terms of what we should expect to win here or lose? Okay, seeing some no's. Anyone feel free to type an explanation for that. Yeah, they each have the same probability. The concept that's important here is they are quote unquote identically distributed. So like the distribution of the different outcomes that can happen is the same for each number you bet on. Okay, so now the more interesting question. If we place a £1 bet on any number on roulette, what is our expected profit? What is the expected value of the amount we make? Yeah, that's right, Owen. Yeah, every slot has an equal chance, assuming the wheel is choosing each with the same probability. Okay, so if you think you know the answer, feel free to type in chat what you think the expected payoff from roulette is on a £1 bet. You're going to need to use the formula that I've given for expected value at the top. Okay, so the list of numbers, so A1, A2, and so on are numbers. These are the possible values that the random variable can take. So for a fair dice, A1 is 1, A2 is 2, and A6 is 6. So N is 6 because there are N different outcomes. And the PI is the probability that the value takes AI, the value AI. So for a dice, all of the PIs are 1/6. Okay, so someone's saying 0. Someone's saying 18. So first of all, then, if there's some confusion, let's try and work out together what are the different values that our profit can take from a bet on roulette. So there are two things that can happen. What do we win if we win, and what do we lose if we lose? Type in chat. What do we win? Okay. So one of the values, correct, is okay. So there's a yeah. So if we win, we're going to win £35 because the 36 we get back includes our original bet, and if we lose, we lose £1. So if X is the amount we win on roulette, it can take two values. It can take 35 or it can take -1. So next we need to ask, what is the probability that our winning is 35? Type in chat what you think the probability that we win 35 is. Okay, I'm seeing a lot of people saying 1/36. You might want to recount. Yes, that's correct, Phoebe. So because of the 0, there is a 1/37th chance we guess correctly. Cool. Okay, and then the probability that we get -1 is then going to be okay, 36/37. So we can now plug these numbers into our formula for expected payoff. So we have a 36 out of 37 chance of winning -1, plus a 1/37th chance of winning 35. Does anyone want to add up what that gives you? Who's asking this? Unknown user. Does 0 give the casino an advantage? So no. If the expected value was 0, the casino would be like indifferent to placing the bet because on average they win nothing. But what we're about to show is that actually our expected value is negative, which means that it is an advantage for the casino. Yeah, that's correct. Someone, 20 Lawsons, has said that. Yeah, so the average is minus 1/37. Okay, so the takeaway here, yeah, that's good. Yeah, so if X is the payoff of the game, then we either get plus 35 or minus 1. We're losing 36/37 of the time. And then the payoff is minus 1/37. So every time we put £1 down on the roulette table, we just lose 3p on average. Cool. So this is a good opportunity to introduce something called the law of large numbers that you might have heard of before. It's not important if you haven't. So imagine that we're in the casino and we're making multiple £1 bets on roulette on separate spins. So everything is independent of each other. And we're going to ask, what is our average profit from the spins we've made? So say on our first spin, we lose. And so we lose 1. And then on our second spin, we lose. So we lose 2. And then on our third spin, we win. So now we're up 33. And we've had 3 spins. So in this example, our average profit would be 11. And therefore, S3, which is the average of the first 3 spins, would be 11 in this example. Okay. So this is like we sample n goes from roulette and we see what our average score is. And what the strong law of large numbers states is that these averages that you calculate as you keep on spinning the wheel are going to get closer and closer and closer to the true average, which is minus 1/37. So if you play a million bajillion spins of roulette, on average, you just lost 3p per spin. So your profit is like a million bajillion times 0.0. Your loss is a million bajillion times 0.03. Okay. So just to check everyone understands this, can everyone type in? Yeah. So 20 Lawsons, that's correct. I was going to say, if you played 37 £1 bets on roulette, how much have you lost on average? Type it. Feel free to type an answer in the chat. Yeah. So you would have lost £1 or gained minus £1, I guess, if you want to be pedantic about it. Yeah, cool. You'd lost £1. Cool. So what the strong law of large numbers says is that the probability that Sn converges to minus 1/37 is 1, i.e., it's guaranteed to take place if you sample far enough into the future. Okay. And this doesn't just apply to roulette, but this applies to a very large class of random variables. So, for example, the average spin on a dice, if you roll a dice a million bajillion times, you get on average 3.5, and it gets closer and closer to that value, and that's guaranteed to happen. Which means if you were to play in a casino at roulette infinitely many times, you would just be guaranteed to have lost 3p per bet. Cool. Okay, what actually happens in the casino, though, does involve some randomness. So that's obviously not being taken into account of by just like thinking about the average, because you might win and you might equally lose. And for small values of n, for small numbers of spins, there is some randomness that we would like to measure. So we'd like to have a measure of like how much randomness there is in like some observations that we do. Okay, so you can see in this slide, I've got a picture of 2 different distributions of numbers. Okay, so one of them is quite narrow and is quite tall because all of the values are coming very close to that average value. And then we have one fatter one where the values are more spread out. So we would like to measure how much variance there is, or how much like fluctuation there is in the kind of value that we observe when we sort of measure things. Okay, so which of these 2 pictures, the pink or the blue, do you think has the most variance in its distribution? Feel free to type in chat what you think. Yeah, everyone agrees that it should be the blue that has the most variance. So what we need, if we're going to like analyze these like rigorously like a mathematician, is we need to define what is the variance of a distribution of numbers? So the technical term here is variance, and it's loosely speaking, it's the average distance of a variable from its mean. Okay, so in the roulette example, the mean is 1/37th. How far on average is a spin of roulette from that mean? So the formula is given here at the bottom, and we're going to do the expected value of the squared distance that x is from the mean. Everyone thumbs up if they can read the formula, understand what it says. So it's the average distance from the mean. Okay. And then some of you might have heard this expression that thing is also equal to the mean of the square minus the square of the mean. So there's a second formula which might be a bit more useful for actually like calculating it later on. Okay, everybody seems happy, so we're going to move on. So before we do anything else, we need to go through some basic properties that the expected value and the variance satisfy that we're going to need in the calculation we're about to do. So imagine we have two random variables that don't depend on each other. They're completely independent. So the value that one takes doesn't influence the other. You can think of this as like flipping a coin and rolling a dice, or rolling two different dice, or something like that. Okay. So the first property that we need is quite intuitive. It says that the expected value of a sum of random variables is the sum of the separate expected values. So for example, if you roll two dice, you expect to get 7 because that's the sum of 3.5, which is the value of each dice. So this property is called linearity, something you might see later on in your maths career. The second property is that it kind of has this quote unquote like multiplicative property, which is the expected value of 2 times this dice roll is twice the expected value of 1 dice roll. So for example, if you roll 1 dice and double its value, you expect to get 7 because that's twice the value of the expected value of the original dice. Okay. Now, what about variance? So variance actually has the same linearity property, that the amount of randomness in the sum of two independent random variables is the sum of the amount of randomness that they each have. That's a bit of a convoluted sentence I said. Can I get a thumbs up if everyone feels happy with what I said? Or if anyone's confused, feel free to say. Getting some thumbs up. So we're thinking of variance of x plus y as like how random is the quantity x plus y? Like how much noise is there when we measure this thing? And what we're saying is that the amount of uncertainty in the sum of variables is the sum of the uncertainty in the individual variables. That's kind of the point of this. And I should say this is only true if the variables are independent. Otherwise, there's going to be some dependence between them and it doesn't work. Now, because of the square that we had in the previous formula, we've measured squared distance from the mean. Actually, when you multiply a number, a random variable by a number, the amount of variance there gets multiplied by the square of the number. So for example, if we wanted to do the variance of 2 times a dice roll, that's actually 4 times the amount of variance there is in one dice. So like homework for you would be to check all these formulas from the definition of expected value and variance that I gave you already. But it's not super interesting to do, so don't worry about that if you don't find that interesting. So now we're going to apply these. And what we're aiming to do in this whole section is calculate the probability that if you play 100,000 spins of roulette, what is the probability that you come out losing money? Because if you play one spin, it is possible, and like 1/37th of the time, you're actually just going to come out up £35. But the point is we're going to show that the more and more spins you play, the more likely it is that you lose money overall. And we're going to be able to calculate how much money you should lose or what the chances you lost money and things like that. Yes, Prisha, you will be shared a recording later on. If you're wondering if you can come back and check what properties I said to prove, then they'll be the slides will be shared as well. Okay, cool. So first of all, we're going to do some exercises that use these properties, which I'm going to copy onto the next slide as well. Okay. So we're going to have a sequence of random variables. You can think of these as separate rolls of dice or separate spins of the roulette wheel and so on like that. They're all going to have the same distribution. So we're using the same roulette wheel. They all have the same average. So the expected value of each of the xi's is just m. So for roulette, this m is -1/37. Okay. And we're going to assume that they have the same variance as well. We haven't calculated the variance of roulette, but it's about 2. So in this case, S is going to be √2 approximately. Okay. So if we define Sn as the sum of the first n random variables, what I'd like you to have a think about is what is the expected value of Sn using the rules that we have below? And what is the variance of Sn? So have a think about it for a few minutes. Feel free to type an answer in chat and then we'll talk about it. So remember that your answer should be in terms of M and S. Okay, yeah. So Ned has said the correct answer. So because of the fact that the expectation of a sum is the sum of the expectations, we're just going to get that the expected value of S is m plus m plus m plus m n times, which is mn. So lots of people are saying the correct answer there. How about the variance? What is the variance of Sn? Yeah, I can see people saying the correct answer again. Yeah, that's good. So yeah, we just have n variables, which are each contributing s squared to the variance. So the variance is added up, we get ns squared. That's good. Okay, so now we've got to do one final step before I can state the result we need to use. Okay. So as we all said, that the expectation of Sn is just the sum of the expectations, which is n times n. The variance is the sum of the variances, which is n times s squared. So now, what we're going to do is subtract mn from Sn. We're going to divide by square root of n times s. Now, I'd like to know what is the mean of this quantity, as in what is the expected value, and what is the variance. And we're going to use the same rules that we saw before. So I'm going to give you 10 seconds to write down the formula we're looking at, and then I'm going to flick back so you can see the rules we have to play with. Okay, so I'm going to change it in 5. Okay, I'm flipping back to the rules. So if you think you have an answer, feel free to type in chat. This one's a bit harder. I'll give it a minute, otherwise we can just talk it through together. Okay, I think we'll talk it through together then if people aren't so sure about this one. So, first of all, let's start with trying to work out the mean of this. So what is the expected value? Well, first of all, we need to use the property, the third property on my list, that we can factor out the number part to the outside of the expectation. Okay. So in this case, the 1 over square root of n times s can come outside of the expectation. Okay. So that's the first step. So we get 1 over square root of ns times the expected value of Sn minus Mn. Everybody happy with that so far? Thumbs up in the chat if you understood what I said. Okay. So now all we need to do to finish the... Okay, cool. So now all we need to do to finish the calculation is to find out what is the expected value of Sn minus Mn. Now to do that, we can use the linearity property, which is that the expected value of x plus b is the expected value of x plus b. So this is also contained in the third. This is also contained in the third bullet point. Everyone see that? So actually, the expected value of Sn minus Mn is just 0. Is that believable to people? So if we roll a dice and subtract 3.5 from whatever number of dots we get, on average we should get 0. I think that makes sense. Do people believe what I said? Okay, cool. So the point of subtracting the Mn was that we've shifted our distribution, so it's now around 0. Okay. So we've done the same thing as rolling 2 dice and subtracting 7 from our answer. So now on average, we should get 0. And what we also want to do is scale the amount of variance that we have by just dividing it by a number. Okay. So if I were to square the denominator, I get ns squared, which is exactly the variance of the numerator now. Because the variance of the numerator we already calculated is ns squared. So the reason this denominator has been chosen is this is the scaling that moves our distribution to have variance 1. Okay, so this quantity I've written down on the board actually just has mean 0 and variance 1. Thumbs up if you're happy with what I've said so far. Or if you want more explanation, we can. Okay. So okay, nice. Okay. So what we did was we shifted our distribution by its mean, so it now has average 0. And by dividing it, we stretched the distribution down, so it has variance 1. We stretched the amount of randomness we have. So for example, let me give you a ridiculous example. So if I flip a coin and I write down 1 if it comes up heads or 0 if it comes up tails, then the average thing I write down is a half. So the variance is the average distance from the mean, which is then also a half. Okay. So flipping a coin has variance 1/2. Okay. But then if I was to divide it by a million, so if I write down my number and divide it by a million, I will get something which is always extremely close to 0, which basically has no variance at all. It's just 0 plus 10 to the minus whatever. Okay. So by dividing by a number, you can decrease the variance of your variable because we just make it smaller. All of the values it can take are squished down so that there's less variance there. And the point of dividing by root n times s is that that is the amount that you need to squish by to make the variance exactly 1. Okay. Okay. So we now know that this quantity has variance 1 and mean 0. And okay, so if you want to see why the variance is exactly 1, I'm going to try and write on my... Okay, this is going to look disgusting, but I'm using my finger on my laptop screen. So, okay, so variance of this thing divided by root n times s times the thing on the top. Okay. So the first thing we need to use is the final fact here that when we have a constant, we can bring it out, but we have to square it. Okay. So in this case, it's squared. So in this case, we're going to bring out a 1 over n s squared. And then we're left with a variance of Sn, which is just ns squared, so we get 1. Okay, so it's because of the squared. Yeah. Okay, cool. Let's move on. So can I get a thumbs up in the chat if anyone knows what the normal distribution is, or a bell curve, or a Bell distribution? People heard of this? Okay, cool. So normal distribution looks like the picture I have on screen right now. So it's kind of like peaked in the middle, and it tails off to either side. So this distribution comes up an awful lot in science, and like if you go out on the street and you measure a load of people's height and you plot them all on a histogram, you're just going to get a normal distribution. It comes up everywhere. And what I'm about to tell you is the reason why you see the normal distribution absolutely everywhere. So it's a theorem, and it's called the central limit theorem. It's kind of like, first you do the law of large numbers. Central limit theorem is like the next best thing in probability. And it tells you that so we know that this thing I've written down, the average of the first n things, has mean 0 and variance 1. But what the central limit theorem tells you is that as n gets bigger and bigger and bigger, this quantity actually gets closer and closer to being normally distributed with mean 0 and variance 1. So the average of your n samples gets closer and closer and closer to a bell curve. And as n goes to infinity, it just becomes a bell curve. So that's the central limit theorem. So what we're going to do is apply this to try and calculate the probability that when you play 10,000 spins of roulette, that you come up a loser, as in that you lose money overall. Okay. So I'm not going to try and rigorously state the central limit theorem. That's going to have to wait until your first year of uni, unfortunately. But we are going to assume that this thing is roughly normally distributed. Okay. And then, so the fact that we would lose after our 10,000, be losing after our 10,000th spin of roulette, would be saying that S of 10,000 is less than 0. Does that make sense? Thumbs up if everyone believes that we lost money if S 10,000 is less than 0. Yeah. So if anyone's unsure about that, the point is that S 10,000 is the sum of our profits from our first 10,000 spins. And we lost money if our profit is negative. Okay. So let's go. We're going to calculate. So we know that each spin has mean. Type in chat. What is the mean? What is the expected value of each spin? Yeah. So each spin has mean 1/37th. Good. And I plunked around on my calculator earlier, and I calculated for you guys that the variance of each spin is 1.918-ish. We'll just use the approximation for now. So that's the variance. So now we're going to subtract 10,000 times our mean, which gives us this numerator here from S 10,000. Okay. And when we divide by square root of n times s, we end up dividing by 10 times the square root of 1.918. Okay. S 10,000 is less than 0 if and only if this inequality is true. So I did the same thing to both sides of the inequality over and over again. I subtracted 10,000 times minus 1/37th, and then I divided by the same thing. Everyone happy with what I've done so far? Type in chat if you're confused or if you're happy. Happy? Okay, cool. So the event that we lose money, i.e. S 10,000 is less than 0, is exactly the same as if this thing on the left is less than what turns out to be about 1.95. Okay. So how do we calculate the probability that the thing on the left is less than 1.95 Well, we're just going to use the central limit theorem. So 10,000 is pretty big. So this thing on the left has got very, very close to being the distribution of a normal 0, 1 distribution. Okay, so it's got very close to a bell curve. And we can just like now look up online or on a table for the normal distribution. What is the probability that a normal 0.1 is less than 1.95? And this is an approximation. It's very, very good approximation to the probability that we lost money on the roulette. And if you Google this or put it in your calculator or something, you find out that it's approximately 97% likely that after 10,000 spins, you come up having lost money. How do you do it on a calculator? So I don't know. It depends. Depends what calculator you have. But if you have one of these, like I had like a white Casio thing, and there's like a stats section, and it can tell you the not cumulative distribution of a normal. So what the cumulative distribution is, it's a function. I can define it for you. So the function is defined as f of x is the probability that normal 0.1 is less than x. Okay. And so some calculators just have this built in, and you would just plug in 1.95 and you should get out something like 97%. Otherwise, I just Googled like normal cumulative distribution function or something, and it came up. Anyway, so if you're interested, an interesting extension for you guys is to say, what if we replace 10,000 with some even bigger number? How quickly does this probability get closer and closer to 1? Because we know by the law of large numbers that as you increase the number of trials, your average winnings will converge to negative number. And so the central limit theorem tells you how quickly your average winnings converge to being a loss, basically. So it would be interesting if you even want to plot a graph of this against the number of spins. That would be a pretty interesting project for you to work on. Okay, so I think this is a natural place to stop for today. I'm going to come back to extension opportunities in a minute. I'd just like to give you a little teaser of what we're going to be doing on Thursday. So we're going to move away from the probability a little bit on Thursday, and we're going to talk more about multiplayer games. And we're going to be talking about games in which people are not working together. So non-cooperative multiplayer games. And what we're going to be thinking of is, what does it mean for a strategy to be optimal in a game? What does it mean for you to be doing the best possible thing? And if everyone is playing as optimally as they should, what kind of moves do they do? Does anyone have a guaranteed win? These kind of questions. So we'll start by looking at some simple games like rock, paper, scissors, sort of deciding on some good definitions. And what we're going to talk about is a definition called the Nash equilibrium. Okay. For now, though, I'm going to give you a couple of ideas of what you can do to extend what we did today, and then I'll take some questions. So a fun thing you could do would be to actually just like simulate taking some samples and taking the average and try and verify that the central limit theorem at least looks like it works for yourself. So you could do that either by literally just sitting down and rolling a dice a whole bunch of times, or you could write some like code if you learn Python or R or anything like that. You could write some code to roll a bunch of dice for you, which would save you lots of time and plot some nice graphs, and you should be able to get this normal distribution curve out to see that it like central limit theorem sort of makes sense. Yeah, it does. Hang on, I'm going to answer all these questions in a moment. Another idea for a little project for you would be, instead of doing the analysis we just did with roulette, can you try and do similar things for other like common casino games, for example, blackjack or baccarat? A really fun thing to do is to try and learn about like the maths of and the probability associated with how card counting actually works. Try and figure out like, can you justify with these probability tools that I've told you that card counting actually increases your chance of winning? Things like that.